We are going to start with the presentation predicting the BI-RADS lexicon for mammographic masses using hybrid neural models. And Juanita Hernández is presenting. Please start.
Thank you. Good afternoon. My name is Juanita Hernández. I am a student at the Estado de Tamaulipas in Mexico. I will talking to you about the paper entitled Predicting the BI-RADS Lexicon for Mammographic Masses using Hybrid Neural Models. I will start the presentation by explaining the general analysis performed by a radiologist to diagnose breast cancer and its association with the design of computer-aided diagnosis systems. Once the mammography is taken, the specialist analyzes the mammography based on the BI-RADS standard, from which a breast lesion is described. Afterward, the radiologist determines the potential risk of being breast cancer. To suggest the patient two cases, to perform an additional medical examination in the benign case or a biopsy in the malignant case. Most CAD systems are developing, focusing on the final phase of this analysis, perform a final classification into benign and malignant class. However, what happened about the intermediate stage related to the BI-RADS analysis? It has been found that the CAD system has several challenges to solve, such as developing medical tools to generate reports compatible with the BI-RADS and solving the issues related to these systems' explainability. These are the motivation to develop new approaches based on the hybrid neural schemes. I will talking about this later. First, I want to talk to you in detail about the BI-RADS analysis. The BI-RADS include a lexicon to describe the tumor shape and margin, and also the breast tissue composition, which involves a high risk of developing breast cancer. Benign lesions tend to have more regular shape, a well-defined margin, and homogeneous texture. But when a lesion begins to deform and overlap with the breast density tissue, make a complex the breast cancer analysis in mammography. The proposed hybrid approaches are able to describe the tumor shape and margin and also the breast density composition. These are denoted by CNN-MLP and CNN-DMN because they include two stages. In the first stage, an automatic feature extractor is carried out by a pre-training convolutional neural network. And in the last stage, a neural network classifier is used. There are three problems to be solved by these approaches. Multi-class classification in shape attributes, round, oval, lobe, and irregular. The margin model in speculated and non-speculated classes, and in the three classes of mammographic density, fat, glandular, and dense. The dataset includes 1,304 mammograms to evaluate the tumor shape, 1,765 for margin, and 502 for density. This image requires an image preprocessing, segmentation for the shape analysis, tumor signature extractor for edgy analysis, removal of the pectoral muscle and the surrounding area in the breast density for texture analysis. Also, for the transfer learning using AlexNet, the mammograms in grayscale were resized and concatenated to form 3 channels in order to introduce those images in the input layer. Subsequently, the convolutional and max pooling layer are preserved. Only the features of the last layer of max pooling are used as feature vectors to train a neural network. In this case, 2 types of neural networks were used. The multi-layer perceptron network, denoted by MLP, and the dendrite morphological neuron, denoted by DMN. The setting used is shown in the following table. The AlexNet settings were established by trial and error, and the other parameters, such as the number of neurons in the MLP model, were found by grid search. The proposed model were evaluated using 10-fold cross-validation. The classification index used are the following: accuracy, Matthews correlation coefficients, area under the curved rock, sensitivity, and specificity. The table shows the results obtained by the 2 proposed methods to predict the BI-RADS in terms of shape, margin, and density attributes. The results indicate that both methods obtained similar classification performance index, obtained around 91 and 95 and 91% for shape, margin, and density classification models. In terms of accuracy, the p-value obtained by Wilcoxon test indicates that there is not a significantly difference between the 2 methods in all models. It's worth mentioning that the number of hidden neurons in the MLP was 11 in the shape and the density model, and 12 in the margin model. Finally, the 3 tables show the confusion matrix obtained by the 2 proposed methods to evaluate the 3 models, shape, margin, and density. Each entry in the matrix represents the mean of the 10 cross-validation experiments. The diagonal of the H matrix shows the number of correct cases classified. The shape model confusion matrix reveals that the most notable overlap between attributes is produced between oval and round patterns than the other types of shapes. This effect is because these patterns are similar. On the other hand, the margin model confusion matrix presents a more overlap between attributes than the shape and the density model. This trend is because of the low contrast in the interface between the tumor's margin and the nearby glandular tissues. Finally, the density model confusion matrix presents the least overlap between attributes compared to the others model. This is not overlap between fat and dense attributes, since the contrast between 2 patterns is high. However, the overlap between patterns transition is high, particularly between fat-glandular and glandular-dense. This paper introduced two hybrid neural models for predicting the three terms of the BI-RADS lexicon for masses, shape, margin, and density. A CNN and two neural models proposed the hybrid models denoted as CNN-MLP and CNN-DMN, which obtained a competitive classification performance for all the classification index without significant differences. The DMN architecture is versatile since a single neuron can generate non-linear decision boundaries. On the other hand, the MLP requires at least one layer of hidden neurons to develop nonlinear decision boundaries. This aspect can increase the computational cost of training in MLP, whereas in DMN, the cost of training can be reduced because of its geometrical exploration property. The proposed method can provide radiological language responses like a second opinion regarding the shape, margin, and density attributes useful for decision making. Future work considers developing a CAD system that includes these models for breast lesion classification in benign and malignant cases. Thank you for your attention.
Thank you very much for your presentation. If there are any questions, please, you can click on the icon for raising your hand, or you can write on the chat, please. Okay, I can see a hand, please. Make your question.
Hi, Juanita. Very good. I like your presentation. And I have a question. It's about the classifiers that you attached in the final of the convolutional neural network. Is it possible to use another classifier instead of these neural networks?
Yes, Professor. Is able to use other kind of, for example, machine learning algorithm to predict the other pattern classification, for example.
Okay, and it is difficult to change the classifier by another one? Or
no.
It's easy?
It's easy.
Okay.
I think the maybe the difficult of the develop a new scheme to classify pattern other pattern classification is in order to tuning the parameters in the CNN, because this model is pre-trained using different kind of objects, and when I can use that for other kind of patterns, the network need to tuning the parameters in order to classify other kind of problems, different the conventional objects, for example, cats or dogs.
Oh, okay. Okay, thank you, Juanita.
Thank you.
I have a question, Juanita. Have you compared your work with other type of classifiers or any other way of detecting these tumors so that you can tell me how efficient it is compared to other methods?
In this case, we present two approaches in order to compare the performance between two kinds of neurals approach. In the literature is a little work to try use convolutional neural network to predict the shape and margin and density, particularly in margin classification is low the works that report their results about this problem. In this case, we consider that its work is an an input in the state of art in order to solve this kind of problem.
Okay, thank you very much, Juanita. If there is there any other question, please? Okay, if there is no other question, we are going to continue with our next presentation.
Okay, thank you for your attention. Thank you, Professor.
Okay, we are going to continue with detection of temperature contours on the thermal distribution generated by ablation micro-coaxial antennas. Are you ready, please?
Yes.
We can see your presentation. Okay. We cannot see it now.
Can you see the presentation?
No, not now. Ah, it's coming. Yes, now we can see it.
Okay. Good afternoon, everyone. My name is Texar Javier Ramírez Guzmán, and today I'm going to talk about the article Detection of Temperature Contours on the Thermal Distribution Generated by Ablation Micro-coaxial Antennas. And thank you all to be here in this presentation. Okay. The index of the presentations will be in 4 sections. The introduction about the ablation generated by micro-coaxial antennas and edge detection, the methodology proposed to the image processing, the results obtained with using the methodology proposed and in the thermal images, and the conclusions about the temperature contours. As introduction, we can see that the micro-coaxial antennas have been studied to treat bone tumors as an alternative treatment. These antennas burn the tumor raising the temperature inside this tumor. So thermal ablation is defined as the direct application of heat in the tumor to cause its destruction. For that reason, we need temperatures between 60 degrees Celsius and 100 degrees Celsius to kill the tumor. So this antenna is placed inside the tumor to apply electromagnetic energy and burn the entire tumor, as we can see in the figure 1. However, there are some problems during microwave ablation treatments. For example, one of the main problems is the inability to know the contour of the temperature distribution generated by this antenna. As we can see in the figure 2, each antenna design generates a different temperature distribution. To visualize this temperature distribution, we can take a thermal image during the experiments. However, the thermal images are not enough to detect the difference between using one antenna or another. So, if the contour of the temperature distribution of the antenna can be known, the reliability of microwave ablation treatment can be improved. Now, edge detection filters allow locating areas where sharp intensity transitions occur. This type of filters can be used as tools to identify zones and borders between different intensity of a study area. The extraction of edges is based in the extraction of pixels with the high variations in the intensity scale. So these variations in the intensity for extraction edges, contours, and corners can be realized with different algorithms. For example, in this case, we use the Sobel operators. The Sobel operators detects is a algorithm to detect use it to make image processing. Along with Canny and Prewitt, Sobel is one of the most popular edge detections algorithms used in today's technology. So the main goal of this work is the development of an algorithm to obtain the contour of the temperature distribution generated by micro-coaxial antennas, using thermal image as a visual aid to understand how biological tissue is damaged during microwave ablation procedures. So the methodology proposed. The proposed solution to obtain the temperature contours of the antennas are the next steps. The first step is to obtain the thermal image of each antenna. The second step is to make a RGB to IHS conversion to do the image processing in the intensity scale. The step 3 is to apply a Gaussian filter to reduce the noise in the image. The step 4 is calculate the intensity gradient of the image using the Sobel operators. And the last step is to generate a black and white contour masked by using a threshold function. So, to obtain the thermal image, 4 different micro-coaxial antennas previously studied were used to generate thermal ablation in multi-layer phantoms. In figure 3, we can see the experimental configuration to obtain the thermal image, and the parameters were 5 watts of input power per 5 minutes of radiation, and a thermographic camera was used to generate the thermal image. Once we obtain the thermal image, RGB to IHS conversion is done. This conversion makes a RGB image in intensity, hue, and saturation. the image processing is done only in the intensity channel without processing the channel H and S. And in the figure 4, we can see the intensity channel of the thermal image. Okay, in some cases, the image presents irrelevant details as black or white pixels due to the transmission errors of the storage. And for that reason, a Gaussian filter was implemented to reduce the noise in the image. To make this filter, we need to do the convolution between a 5x5 kernel and the intensity image. So up to this point, we can observe the temperature contour of the thermal image. However, it presents very little definition to the details. That's the reason why the next step is to calculate the intensity gradient of the image to obtain an image with a more defined contour. This intensity gradient was calculated using the Sobel operators, as we can see in equation 3 and 4. Now, the next step is to make a zoom between the image with the Gaussian filter and the intensity gradient to obtain a new image where the temperature contour presents values close to 0 or black pixels. And as we can see in the figure 7C. And the last step is to perform a threshold to obtain a binary mask where the pixels with the values of 0 represents only the temperature contour and the white pixels the background of the image. This threshold is done in the image A. For example, if the pixel to evaluate have a value less than or equal to the minimum intensity value, it means that it's part of the contour. In another case, the pixel is part of the background of the image. With this threshold function, we can generate a black and white mask that will be positioned on the original thermal image. The results. Now, with this image processing, now we can see more easily the difference between using one or another antenna. For example, the MTM and the MTMC antenna generate a circular shape, and on the other hand, the DS and the DSC antenna generate an elliptical shape. And with this image processing, now this provides a visual context in the study of the micro-coaxial antenna's behavior. If we have to apply a conventional edge detection as a canning method, it is observed that it detects irregular edges that are not part of the temperature contour. That's why if we use only Sobel operators allow adapting edge detection to a specific target. In this case, the temperature contour of the micro-coaxial antennas. And as discussions, this work is the first approach to detect the areas that reach the ablation temperatures generated by the antennas and to know the amount of damaged tissue, and the importance of detecting all the pixels that make up the contour of the temperature distribution will allow future work to calculate the area of damaged tissue. And the conclusion of this work, this algorithm allows to obtain the contour of the temperature distribution generated by micro-coaxial antennas by reaching temperatures above 60 degrees Celsius. And the future work work will include the contour detection based on the temperatures reached in the experiments to calculate the area of the damaged tissue. And that's all. Thank you very much.
Thank you very much, Texar, for your presentation. We are going to start with questions, please. You can raise your hand or write your question on the chat.
I have a question.
Yes, please.
I have two questions. The first one is about the data that you obtain from the camera. You obtain the image from the camera, but also I think that also the camera gives some information about the temperature in each point of the image. So how do you justify the use of the image processing instead of using the data that can be obtained from the camera? Do you know what I mean? Because I think that the camera gives you the temperature information for each point, but why do you use the image instead of the data that gives you the camera? Is there any advantage of using the image instead of the data?
Okay. Yes, when we do the experiments, we can obtain the thermal image, and the thermal image gives a temperature matrix. But in this case, we just focus in the RGB image because we only want to know the shape of the thermal distribution. If we want to know, for example, the tissue damage, we need to make this processing in the temperature matrix.
Okay. Another question is about about using the infrared camera, because when you use this kind of camera, you obtain the temperature and the surface of the object. So can it be used in clinical application, or what kind of application are you thinking about your image processing? Because I think that it's only on the surface of the object, not inside the tissue. Or
Okay. Yes, that's a problem because the thermal camera only obtains an image from a surface. So in this, we just want to know the temperature contours to detect the amount of necrotic tissue. And with this, evaluate the treatment times and the power input. It's only that we want to know.
But you can use it only in phantoms, I think. You cannot use it in a clinical application.
No. It's for now. It's only in phantoms. Yes.
In phantoms. Okay, that's all. Thank you very much.
Thank you.
Thank you. I can see another hand raised.
Yes, I have two questions. Please. In the image where you compared your results with both results with the canning method and all the processing you made, why the canning method doesn't work as good as the processing you developed in the temperature contours detection?
Okay. That's because the canning method allows to obtain edge or corners. For example, corners of a house or corner of a bridge. But in this case, we want to obtain the contour in a surface. That's why the canning method doesn't work well in this application.
Okay, and the second question is, in ablation treatments, why is it important to know the temperature contours of the image obtained?
Okay, this question is a little similar as the last question. why is important? Because by knowing the temperature contours, we can detect the amount of necrotic tissue. And with this, we can make a plan to evaluate the damage in the tissue.
Okay, thank you, and thank you for your presentation.
Thank you for your question, Jorge. I have another question. As you mentioned with Dr. Vera, now you are working with phantoms. And how much does it improvement is going to be in clinical applications once you know your results? What is the advantage in the final application in clinic according to your results?
Okay, for now, if we want to apply this method in clinical treatments, it's not efficient, because if we use a thermal camera, we need to make like a cut in the body just to obtain a thermal image. So if we want to do this kind of processing in clinical treatments, we need to work with another kind of image. For example, ultrasound. That will be, yeah, that's the reason why now we just want to know the shape of the damage.
Okay, so you are going to translate this information into real tissue. You expect the real tissue to behave very similar to your phantoms.
Yes, that's what I expect. Yes.
Okay, thank you very much. Any other question, please? Okay, I can see a hand raised. Please make your question. Ruben?
Hi, Texar. Yes, Texar. I want to know in the graphic you presented that the A, B, C, and D antennas. Maybe I didn't know, but I want to know more or less the scale of these graphics. How is it? 1 millimeters, less than 1 millimeters in the real experiment.
Okay. Yes. In these antennas?
Yeah, this one.
What's your question, please? Again?
The scale, the scale of the graphics. How much? The scale.
Okay. The antennas is, if I don't remember, is 12 millimeters.
I mean in the graphics, the circular wave, for example. What is the scale?
Okay. The image is 204 pixels for 320. The image.
And
but if we want to know the contour, the dimension of the contour.
Yeah, of the area in the real life, or how it's represented. There is.
Okay. In the real life, the problem with this image is that we can do a processing to obtain the area, because for now we are not taking temperature data. So for now we just see the contour, but the areas just using this image is not possible to do it. Making this kind of processing.
Okay, thank you.
Thank you, Ruben, for your question. Any other question, please? Okay.
José Hugo?
Hugo?
Sí,
please.
hola, hola. Hola, hola, ¿qué tal, Texar? Una pregunta para darme una idea del tamaño de tus áreas. ¿A todas las antenas les aplicaste la misma potencia para hacer para obtener estas imágenes termográficas? ¿O fueron diferentes potencias a las antenas?
Sí, fueron las mismas potencias. Tanto las potencias como el tiempo de aplicación fueron los mismos para las 4 antenas.
¿Significaría que algunas antenas te dan áreas más grandes que otras con la misma potencia o no tiene que ver?
Sí, de hecho sí, dependiendo del diseño de la antena, algunas pueden generar mayor cantidad de daño en el tejido. Sí.
Ok, sí, gracias.
Thanks, Hugo. Any other question, please? I think we are just in time to continue. Thank you very much for your presentation, Texar. And we are going to continue with our next presentation, which is detection of sore risk regions on the foot sole with digital image processing and passive thermography in diabetic patients. And Rafael Bayareh is presenting.
Yeah.
You can share your presentation, please.
Yes. Is it displayed?
Not yet. It's coming. Now we can see it.
Yeah.
Yes.
Ready. Welcome and greetings. My name is Rafael Bayareh, and I'm the presenter and corresponding author of this paper entitled Detection of Sore Risk Regions on the Foot Sole with Digital Image Processing and Passive Thermography in Diabetic Patients. This work is a collaboration between the CRAN laboratories in France and Simvestaff in Mexico. A brief background of our problem is that diabetes mellitus is one of the problems that affects among population worldwide, and unfortunately every year increases in terms of numbers. A common complication of these patients is the appearance of ulcers on the sole of the foot, which the statistics says that approximately between 15 and 25% of the patient will have these ulcers by several reasons. The most common one is due to inappropriate walking shoes. So given this problem of the diabetic foot, our main goal is to study the surface heat distribution as input of our proposal. For instance, we will call it as a black box algorithm in such way that the output of this black box we will display some areas that could develop tissue injuries related to the heat distribution in order to support an early diagnosis of the diabetic foot plus an ER thermography study. So the proposal in this work is resumed by the following diagram, in which I will explain following each stage, starting by the data acquisition protocol, how the data was retrieved as temperature data, and how all this information was processed by the following stages in order that at the end we will have a binarized error image that will display regions that do not have abnormal temperature areas. So for a start, the acquisition protocol, the sensor we use is Lepton 2.5 radiometric ER sensor. The resolution of this equipment is 80 by 60 pixel. The pixel size is 17 micrometers, and this sensor has the capability of measuring the near infrared spectrum from 8 to 14 micrometers. The special feature of this sensor is that it is possible to retrieve the radiometric data in order to estimate the temperature in the frame region. About our patients, we had a universe n equal 12, in which all the patients were diagnosed with diabetes mellitus without a clinical history of diabetic foot or at least visible anatomical alterations or inflammations. This protocol was approved in the Mexican National Rehabilitation Institute. Our patients were put in dorsal position and the foot was left to cool for 10 minutes as suggested in the passive thermography technique. Afterwards, our ER scanner sensor was put or placed 20 centimeters far from the foot, and we took a frame capture for every patient. Then, the information was retrieved as an array of 14-bit data, in which with a characteristic equation that was developed specifically for this purpose, we can interpret this 14-bit data into a temperature map. At this point, I would like to make a parenthesis to clarify that given an array of values, for example, this array of 3 by 3, it is possible to interpret them as a color image with a color scale. For instance, we can observe that, for example, the lowest value will correspond to the blue color, and the highest value, 9, will be correspond to the color red. In such way, these temperature maps that is an array of values can be interpreted as commonly known as an ER image, in which every color intensity is directly related to the temperature intensity. Given this definition, before we interpret this data, we have processed it before. The first stage was to organize the data by range normalization. It is possible to rescale the amplitude of the data, but the shape of the distribution and the attributes will remain the same. For example, we have an original data as only example that has a scale of 0 to 48. Then after the range normalization, we can observe that the scale is going from 0 to 1. This allows to find several patterns. For example, the first one is that an advantage of ER thermography, infrared thermography, is that usually the objects of interest are warmer or at least colder than the background. In such way, we have found that arranging the data, the values that are higher than 0.8 corresponds to the region of interest. Meanwhile, the values that are below 0.8 corresponds to the background. In this sense, it is possible to apply, for example, a high-pass filter, which we can observe that after this stage, values that are higher than 0.8 remains with their same value, and the rest of the values that are lower we can put in 0. So we can see an example of this process. Not only we can eliminate or segment the region of interest regarding the background, also we can see that with this process we can enhance the contrast of an infrared image, which the region of interest is highly contrast respect the original image. After this process, we could observe that 4 of our patients had possible abnormal temperature distribution. As we can see in this region of the metatarsal area, some region of the fingers, and finally also in the heel zone. Also, we found 6 patients that had a normal temperature distribution. Here I show or display some example of how it looked like a normal temperature of the foot, which supports the hypothesis that not all patients that have diabetes mellitus can develop diabetic foot. And finally, unfortunately, we had 2 cases with origin fault in the acquisition protocol stage because our algorithm in this stage is not capable of segmenting the region of interest because there are some areas that have higher temperature than the sole of the foot. So isolating the 4 possible cases, we can observe in this diagram that first, we start processing the radiometric data interpreted as temperature in Celsius scale. Then it was interpreted as infrared image, and then it was converted into the grayscale intensity domain in order to apply some classical digital image processing techniques to try to detect some regions that could develop injuries in terms of temperature intensity. So once we transform the image into the grayscale, we binarize the image through the threshold method also, which is one of the most classical. The also threshold method is just only a variance within 2 classes. For instance, we have 2 classes, the region of interest and the background. And the variance is calculated as such as a statistic equation, which xi corresponds to the value of intensity of gray levels of every single pixel. Mu is the average of all the image intensity, gray intensity pixels, and finally n is the resolution of the image. After we binarize the image, we have these results. We can find that it is possible to display some regions in terms of temperature intensity. However, in terms of computational methodology, if we want to, for example, detect how many regions exist in the sole of the foot, unfortunately, we will detect several regions because every scattered picture will be interpreted as a single area. So a proposal for solve this problem was finally to erode these binarized images. We propose a structure element in the erode method, in which our structure element was a matrix of 13 by 13 with center X, which our center X is an element 3 by 3 with center white. In such way, we can see in this example that black islands can be turned into a single region, and the scattered white pixels was reduced to a single area. So here I present the results of our 4 patients, in which we can see the sole of the foot represented with a single area that is related to high temperature intensity regard the rest of the sole of the foot. In the metatarsal area, fingers, and also in the heel. So we can conclude from this paper that our algorithm proved the feasibility to display regions with higher temperature than the rest of the sole, which commonly are ready to prone lesions, as an indirect way to relate the gray level intensity related to temperature intensity. Also, these cases can be classified as a normal temperature because it is expected that the food should have homogeneous temperature because it was exposed to passive thermography. It means that the food was left to cool with the ambient temperature, so we should not expect to have areas that have higher temperature than the rest of the sole. As perspective, we can say that retrieving the data could be used as an exhaustive numerical analysis for pattern recognition, which usually in thermography is known as thermal fingerprint. Also to support an anticipated diagnosis based on support systems such as medical thermography. Also, this idea support the hypothesis of processing radiometric data before of applying any classical digital image processing techniques. As acknowledgement, I would like to thank to my French colleague, Bing Fan, the technicians of our laboratory, Hugo Cepeda and Ruben Perez, and finally, special thanks to Dr. Cynthia, Dr. Hector, and Ilse for retrieving information in this paper and the treatment of the diabetic patients. Thank you very much for your attention and time.
Thank you very much, Rafael. We are going to start with questions, please.
Yes.
Any question? Yes, there is a question. Please.
Rafa,
yeah.
You use 2-dimension images, is that right?
Yes, it's right.
2D images, is that right?
Yeah.
You didn't mention in your presentation that you are planning to work with 3D images. So I have one question about it, because what would be the advantages of using 3D images instead of 2D images?
Yeah, I must clarify that this project of 3D images is not totally related to this work, because here I try to present the importance of the radiometric processing. However, the importance of using 3D images or 3D model instead of studying every single image is in terms of time and facility for the physiologist. It means that we can have a single entity that can be analyzed to observe temperature differences some regions that can be inflamed that are not possible to study by single imaging. So to have a single entity could also save time and also give a better interpretation to the medic. Yeah.
I think that you are focused now on the soul of the foot.
Yeah.
Because I think that the damages that can be that the parts that can be affected by the diabetic foot is mainly the sole. But
yes.
Is there any other areas of the foot that can be affected by the diabetes so that 3D images can be more useful or not? Do you see what I mean? Am I clear?
Yes, of course. Some colleagues of our laboratory has also researched about these problems in terms of MACUL's study with digital image processing that also supports this hypothesis that the lesions that are not only appearing or develop in the sole of the foot. This problem of the diabetic foot, in fact, affects in the lower limb. So supporting the idea of developing or displaying also a 3D model it supports the idea that it's important that not only focus in a specific region, that's a problem that remains in the 2D thermography, that only we have a single perspective instead of a 3D model that we have a whole perspective of the lower limb.
Okay, thank you very much. It was a really nice presentation.
Thank you very much.
Congratulations.
Thanks.
Thank you for the question, Arturo. I can see another hand, but I cannot see who is it. Could you
Maria
please?
Fernanda.
Thank you.
Hello.
Hello.
So the position of the foot, does it have any influence on your results? For example, if it's fully like erect or inclined to one side or the other, does it have any influence on the temperature or it's not an important factor?
Yes, it's an important factor. Let me find the corresponding slide. Here we can see in the third case, the right one, that this actually it supports your question. The sensor was not placed exactly in front of the sole of the foot, so we can see that part of the lower limb was captured and had higher temperature. So yes, it is affect in this study. It is fundamental to try to keep it as parallel as possible.
And can you do like a I don't know, like a bait or something to put the feet in, so you can control that? Or
yes,
it's not necessary?
Actually, the foot they are placed in a base that we try as much as possible to isolate the background. However, some areas still are not totally covered. So every day in our laboratory, several colleagues are trying to improve this base. Sometimes we have some designs that are in 3D printed. Also, we use pink foam that is a heat isolator. But yes, that's still a remain problem, not only in our laboratory, in several laboratories that share the same purpose.
Okay, thank you.
Thanks to you.
Thank you, Fer, for your question. I can see another hand raised too, but I cannot see the name.
De la Rosa Eric.
Hi, Rafa. Thank you very much for your presentation.
Yeah.
I have one question regarding the information you presented, like I think it was in your first slide. So you mentioned that you are thinking about your model as a black box one.
That's right.
Can you please explain that a little bit? Why do you think it's a black box algorithm?
Yeah, I presented as a black box algorithm because the input we will have in this stage, it's first a radiometric information. They are data and not image. But after the data is processed by the black box, our black box algorithm, at the end we will have a binarized image. So that's the reason. It's a collection of processes that at the end will help to get islands that in computational terms can be detect the coordinates and also retrieve the temperature information when we compare it to the input.
Yes, I was asking this because, for example, when you compare like your procedure with, for example, a neural network or maybe another kind of machine learning algorithms that are actually like black box models because you cannot really understand what is happening inside their gut, right?
Yeah.
So, but I mean, in your case, it is really explicit the way you are processing your data.
Yeah, I understand. Yeah, I guess I misunderstood the term. Yeah.
Okay. I also a second question would be if you had some cases where at the end of your procedure you ended up with two different areas of interest after applying all these steps.
Yeah. Yeah. I may say that the first region of interest first is the sole of the foot, and then it is intended to segment just only the regions that have higher intensity than the rest of the region, the first region of interest.
Okay, got it. And when you already have this binary image, do you think you can like collect more information from it? Like, for example, counting the number of pixels that belong to certain areas, or how do you think this could be used?
Yes, actually, this is a kind of a spoiler question because, yeah, actually we have retrieved the coordinates of every single white pixel of every island. And comparing to the original temperature map, we can retrieve the original temperatures. So we use this information to compare the average temperature differences. It's mean the next paper I will present. We know in quantitative terms, in quantitative way, what is the difference between the sole average temperature regard the white island.
Oh, okay, that is really interesting. And also, I'm also thinking that you can even go beyond that and, for example, have like a series of pictures for the same patient, like in several sessions, and you will be able then to kind of capture like some progression in the areas.
Yes, of course. And that's a very interesting question because sometimes it is not always exposed, this problem, how patients can be as much as possible constant with their treatments and also their compromise to collaborate with the investigation. No, this protocol, which it was approved by a research institute, unfortunately, not always the patients are constant. So that's challenging that remains beyond any technique we apply, you know. Sometimes there are things that are out of our hand. But yeah, that's an interesting question.
Yeah, so thanks, Rafa.
Thanks to you.
Thank you very much, Eric, for your question. Last question, please, Wilfrido.
Yes, thank you. Thank you, Rafa. I have a question. Did you use another kind of morphological operators? You use erosion, but I want to know if you use another, for instance, closing, opening.
Not really, because once it was the first method I applied and it worked, so I didn't continue checking in another techniques.
Okay, because when erosion makes the image wider than the original. Yes. I don't know if this effect is a problem in your method, because in that case you need to apply a dilation to make the size of the image almost equal to the original one. And I don't know if this is a problem. The erosion becomes wider the area you want to analyze.
Yes, actually, yes, because the most narrow is the area, the more we can retrieve only the temperatures that are related to the abnormal temperature region. If I make it wider, I would have more data, more pixels that are related maybe to regions that corresponds to the normal temperature behavior. So yeah, I try to make it as narrow as possible in purpose to only retrieve the temperature that are, for example, we can see in the third image, that are only related to the most red area.
Okay, thank you, Rafa.
Thanks to you.
Thank you very much for your question, Wilfrido. And thank you very much for the presentation, Rafael. We are going to continue with our next presentation.
Of course.
Okay, we are going to continue with feasibility of producing acoustic frozen waves with limited number of rings. Are you ready, please, to share your presentation?
Yeah, I'm ready. Can you see it?
Okay. We can see your screen, but we cannot. Oh, yes. Now we can see your presentation. You can start, please.
Okay. Thank you very much. Good afternoon, everyone. I introduce myself. My name is Alejandro Rodriguez-Peña. I'm studying Biomedical System Engineering at UNAM, and I'm going to present the article with the following title: Feasibility of Producing Acoustic Frozen Waves with Limited Number of Rings. I am grateful to Dr. Mario Ibrahim for his support and with the other authors who participate in this article. All right, let's get started. Well, this is the agenda, and we're going to start with the introduction. All right, frozen waves are non-diffracting waves studied for the first time in optics, where different investigations establish their main properties, such as stationary wave field, a large depth of field, and static envelope in space. These frozen waves have been obtained due to the superposition of Bessel waves. And thanks to different investigations, many ways of producing focused acoustic fields have been proposed for the implementation of these stationary wave fields. The different studies of frozen waves applied to acoustic have provided important results. Thanks to this, in this work, it was possible to analyze how stationary acoustic field is generated using Bessel transducer with finite aperture and with a different number of rings. The distance between rings, named as curve, was kept in all study constant. The only thing that varied was number of rings, first with a continuous transducer, proceeding to 10, 20, 30, 40, and 50 rings, in order to compare the results of the ideal continuous radiation with the discretizations using a small number of rings. All this with the objective to reach an optimal discretization result that facilitates the generation of frozen waves, and in the future, ophthalmic treatments can be applied to the retina and treat diseases such as diabetic retinopathy. Continue with the methodology. This is a timeline of what...
Can you turn on your camera?
It's not turning on. Okay, give me a second.
It's not yet.
No, I cannot turn it on. It doesn't me allow to share my.
Don't worry. Just continue.
Sorry about that.
You can do it. You can do it when you can do it in the points, in the 3 points.
The 3 points?
And
that's it?
there.
Oh, thank you.
Yeah.
Thank you very much. Well, we'll continue. This is the timeline. And what we do in this article: first, we generate and simulate continuous frozen wave. Second, we discretize continuous reference signal. Then simulate signal and control models. And finally, compare and analyze those results. To generate and simulate continuous Rosen waves, we use a specific technique based on an article by Arturo 2006. After that, we discretize the continuous representation of Rosen wave with the objective of simulate both signals, continuous and discretized, on a controlled computational model to finally analyze and compare those results. Here, PR was used as final function to model the Rosen waves. You can see how it is an integration of a multiplication between J0 and F beta. Alpha is determined with the following equation, where beta is defined by the following transformation, and Q is a constant that restricts the maximum propagation along Z-axis, where J0 corresponds to the first kind Bessel equation and F beta corresponds to spectral function that is determined according to the desired longitudinal pattern. And then substituting F beta in PR, the amplitude and phases for the annular transducers that generate the static acoustic field were obtained, both in the continuous and in the discrete cases, depending on the number of rings in each discrete case. Finally, to generate the Rosen waves, we integrate the difference of the Fourier transformation of the following signal Fc, which defines the longitudinal propagation of the acoustic field, where U correspond to the Heaviside step function, and CP1 and CP2 are constant that correspond to points where the static acoustic field will be generated. Both signals CP1 and CP2 have different depth sheet points in order to obtain a configurable focal point. In this article, L equal 10 and CP1 equal to 4 centimeters and CP2 equal to 6 centimeters. Those values were chosen in order to obtain the acoustic field at the center of our rectangular model. Then the computational simulations were carried out using the finite element COMSOL program. The acoustic pressure was distributed in water along an axisymmetric rectangular 2D model, as you can see. The simulations were carried out with the following parameters: frequency of 3 megahertz and a triangular mesh of size of 1/3 lambda, resulting in 196,100 elements. It is important to mention why we perform the simulation in water. There is an advantage because further analysis can be carried out in similar aqueous media, such as those present in the eye. The simulation for the data for the simulations were later exported to MATLAB with the intention of analyze the result in an objective way. The FM geometry is shown in this image, where, as already mentioned, it was designed to have a maximum C length of L equal to 10 centimeters, and with enough X length to reduce the deflection of limits of the model. Boundaries 1 and 2 of the model were established with an acoustic impedance equal of water. The first simulations defined as continuous or ideal case, where the comparisons with the other discretized cases will be carried out. A single 20 millimeters ring was used at the bottom part of our model. The other discretized simulations with 10, 20, 40, and 50 rings were carried out using an annular Bessel wave distribution. The discretization of the acoustic radiation function was carried out by averaging data in different radial ranges controlled by the length for each transducer. In total, 4 different simulations were carried out with 10, 20, 40, and 50 rings, omitting the result of 30 rings because it was very similar respect to the results of 20 rings, remaining the separation value between rings named before as curve, always constant of 0.01 millimeters. In this image, you can see the case of the continuous signal was discretized in amplitude and phase for 50 annular transducers. Continue with the results. In this figure, section A, shown how the acoustic field is effectively concentrated in the previously defined CP points between 0.4 and 0.6 millimeters, with hardly any dispersion of the acoustic waves along the rectangular model. Also, the present acoustic dispersion can be due to an incorrect destructive interference of the waves, possibly generated because the low frequency that was used wasn't large enough to define a smoother acoustic field. This next figure shows the most significant results made with the continuous signal and with 10, 20, and 50 annular transducer. In this specific figure, the results with 40 rings were purposely omitted because 2D representations of the acoustic field is very similar with the results of 50 rings. So visually, the difference between those simulation results presented in this image seems the most optimal. In the other discretization results, we can observe in B that the simulation carried out with 10 transducer bezel rings, the acoustic field is presented in a chaotic way, with a lot of dispersed energy outside the desired focus, having as main characteristic longer prefocal and postfocal zones, starting with 20 millimeters to the maximum length of the rectangular model, and a considerable amount of dispersed energy along our axis. In the following two cases, C and D, the results of the simulations with 20 and 50 bezel rings are observed respectively. The case of 20 bezel ring simulation is comparable with the 50 bezel ring simulation, because between both cases there is only a small improvement in the delimitation of the acoustic focus and in deeper regions, without considerable improvements in the. Although it should be noted that the simulation with 50 bezel rings, acoustic hotspots are presented in prefocal area along the r=0 axis. This result is very exposed with the following figure, where the acoustic pressure was normalized and compared versus the continuous case. In this figure, we can see the acoustic pressure along z-axis, with black color line represent the continuous reference result, and with the other colors we represent with blue, red, green, and purple the results of 10, 20, 40, and 50 annular transducers respectively. From this graph, we can see an improvement at the focus when using more rings start with 20, with minor variations in the prefocal zone. As explained before, the result when using 50 rings produced some undesired hotspots in the prefocal zone, not presented in other graphs. And the reason of this could be coincidental, since they could be product of some resonances at the specific combination of pressure, geometry, mesh, etc. And they may not be necessarily present in experimental radiators. And finally, with the conclusions, in the different simulations performed, comparing the baseline simulations with the others, there is a tendency for the variation of the field to approach the result with the continuous signal for a large number of rings. We observe significant changes that approach the continuous reference signal. Multiple variations caused by different parameters must be taken into account, as they are mainly the width of the curve and the total number of rings. Therefore, these parameters can be modified until a more accurate approach is reached, and theoretically, although there is no limit of choosing a very large number of rings for the radiator, in practice, the required instrument should be considered. And talking a little bit about the possible applications, in this image, we are showing the results of two different acoustic focalized simulations, both trying to generate a static acoustic field exclusively in the area of the retina. In the left side of the image, A, there's the result of a simulation with amplitude and phases calculated using time at different phases, showing an acoustic focalization on the crystalline lens. And on the right side, there is the result of simulation of Rosen waves in the eye with specific frequency parameters, focalizing all the result pressures successfully on the retina. And that will be all in this presentation. Thank you very much for your attention.
Thank you very much for your presentation, Alejandro. We are going to start with questions. I can see a hand. Mario, please.
Yes. Hello, Alejandro. Congratulations for your work. I have a question. You said something about the final application of your technology. Could you please explain us that to us with more detail, please?
Yeah, sure. Is this part? This part, as I said, is the representation of two simulation in the eye. In these simulations, we are facing challenges such as acoustic run propagation because the eye geometry and the necessity of avoid delicate ocular zones such as the crystalline lens is the principal objective. In the left side is a result of acoustic simulation with only modified time phase. And in the left side is the result of applying frozen wave simulation, and there is focusing on the area of the retina in an optimal way. And these applications, these possible applications are for the future. Principle applying this technique to treat diabetic retinopathy with the objective of focus ultrasonic waves in the area of the retina, specifically at an appropriate frequency that doesn't generate any damage to delicate areas of the eye, like I said, in the crystalline or other delicate areas, to stimulate retina vascularization and possibly having a result, no blindness consequence.
Okay, but in those images, which one is the best? I mean, the letter B or A, and why?
Okay, well, in the left image, we can see, well, it's not the optimal result because all the acoustic pressure is specifically focalized in the area of the crystalline lens. That crystalline lens in the eye is a very delicate area, and focalizing acoustic pressure on that area is not healthy. And in the right image, we can see that applying frozen waves technique, we can see how at a specific frequency, as specific parameters like frequency and C propagation along C axis, we can see how the acoustic pressure is only in the area of the retina, and the crystalline lens area is almost, there is no presence of acoustic pressure.
Okay, thank you.
Thank you very much.
Thank you very much for your question. I can see another hand. Juan Carlos, please.
Yeah, congratulations, Alejandro. Very good work. I have a question. In your model, you propose limits that represent the rings and curves between them. If you pressure the limits on the rings, then the space between them are considered at zero pressure, or how do you consider those space between the rings?
Yeah, those space between those rings, named as curve, there are spaces with zero acoustic pressure. We know that in the reality there is some interferences between those values, but we simulate that, and with that specific value of curve of space between transducers, 0.01 millimeters. In this frame, the acoustic pressure is zero. There is no acoustic pressure.
All right, so they are source of pressure, but with pressure equal to zero then?
Yeah. Yes.
Okay, all right.
Thank you very much for your question, Juan Carlos. Any other question, please?
No more, thanks.
Okay, if there is no other question, we are going to finish this session. This was our last presentation, and I thank you all for your presentations, and I thank you all for attending this session. Thank you very much.
Thank you very much. Goodbye.
See you. Goodbye.
Thank you.
Gracias a todos. Creo que ya terminamos por el día de hoy, ¿verdad?
Ajá, esa fue nuestra última presentación. Entonces,